Welcome to the session of parallel programming. So, in the parallel programming on this session, we are going to get one quick recap of our system design for GPU architecture. Okay, so we learned about the terminologies of various compute units, what are the SIMDs and Schroeder ranges, this kind of things. So we need to see that we are able to properly map all those ideas into a basic architecture because this is a basic architecture diagram that is for any GPU system and it may change from a vendor to vendor and how they opt to design it. So we can still get some level of a simple diagram and understanding of the mapping. So here's what it is. So when you want to see, so here that how it is mapped. So this is a scheduler. So as always, it will schedule all the instructions. But now if we remember that in the specification, we went through the last level cache. So in this diagram, only L2 cache is there, but in a specification of our MH300X that we are using, we have a three level cache. So we have a L3 cache also, which is roughly 256 MB, aside from the L2 cache and the L1 cache. So that's the specification. Now next data. So next data what we have our on hand is like a number of compute units. So number of compute unit meaning this streaming multiprocessor that you see, this complete block, that is the number of compute unit. And we had a count of 304 for our system. So we have a total 304 this such compute unit to execute our instruction set. One more parameter that we have seen is there is a instruction set executor in each compute unit. So in the specs of MH300X, we notice that it has a 4 SIMDs per compute unit. So means here what you see this 3 SIMDs. So basically there are like 4 SIMDs. So this kind of 4 SIMDs, and every SIMD would be able to process the work group, which is as a wavefront. So the wavefront size also we have noticed. So let's look at again with this comparatively for the diagrams and see how it looks. So let's see what are all the features. So the first feature that you would likely to see over here is that the wavefront size, let's see on that one, which is like essential ALU that we have seen in the earlier image. So this is the wavefront size we'll be seeing over here, which is 64. So the arithmetic logic unit that we would be expecting in each SIMD would be the 64. And now here you see like max waves per compute unit is a 32. So 32 waves can be processed. So wavefront size, you can see it would kind of act as a 64, which is like holding in its cache. But when it starts to processing, then it will have processing power of a 32 waves per compute unit. And the size would be 2048 bytes. And what are the number of SIMD we have is a 4. So every SIMD would be able to support the wavefront group of 32 per compute unit, and that's divided by the 4 SIMD instructions. So you can see that basically we will have a 8 waves to process each SIMD. So that is how we can like correlate our logic for our instructions. So this is the L3 cache that we already seen, which is a 256 MB, which is additional from the design generic design architecture. And we have a L2 cache, which is roughly like a 4 MB, and an L1 cache, which is a 32 KB. So this cache would be sitting onto the each compute unit. So and the L3 cache would be something which is shared across all the compute units. So we have 304 compute units. Every compute unit would be sharing this L3 cache, just like a common like global memory. So that's a recap for like our basics and like get familiarize ourselves with all the mappings that is required. And from the next session on, we'll actually try to learn and do more of a hands-on of the heap programming with our basic parallel programming